Our project for Dr. Lyel's Geography 352 class at Texas A&M is a comparative study of LiDAR and point cloud data for TXDOT, who is looking for alternative project planning methods. For our method, we attempted to put our recorded data into a 3D mesh, which we could then model and put into Unity or Unreal. But first, we want to say a special thanks to HTS Advanced Solutions for coming out and providing the resources and equipment for our data collection. It was very kind of them to come from Houston to help us out, and we wouldn't have been able to get as high quality data as we did without their help. So our question was, can aerial LiDAR data provide a higher resolution, efficient, low-cost alternative to photogrammetry for TXDOT project planning methods? And this carries over into our hypothesis, which is by using LiDAR, will we be able to improve the spatial accuracy of the data collection process for TXDOT alternative project planning methodology? For our overview for this project, we first had to go out into the field and collect the LiDAR data, for which we then processed, and then after the data was processed, we were able to compare the LiDAR data to the photogrammetry, and then after that we were then able to take the point cloud data and all the data that we collected and attempt to put them into Unity or Unreal game engines.
We chose this area in College Station because it's a small study area that was done by a former group, and Texas Department of Transportation would also want to do this area due to the erosion of the bridge. The study site is located on the eastern side of College Station along William D. Fitch Parkway. Carter Creek runs under the bridge, which is the main reason that the columns under the bridge are eroded so much. Here you can see two site maps that we created. One is the contour map showing the contour lines along the stream of the creek, and the other is a ortho map so that you can see the overview of the area studied. These eroded columns are the reason that Texas Department of Transportation would want to come in and redesign the bridge using photogrammetry or LiDAR rather than a traditional survey, so that they could create a 3D model of the bridge that they are designing.
For this portion of the presentation, we're going to be talking about the methods that we used in the field to collect our data for this project. All in all, showing up to the side of the bridge, from setup to collecting the data and leaving took only 2 hours, which shows how quick and easy and efficient this is, and as you'll see, the amount of good information and data we got from it. We used two different LiDAR units, a terrestrial for under the bridge and an aerial for the whole area on the top of the bridge. We also used a drone for mounting the aerial unit and getting some photogrammetry, and we also used a series of ground control points that were used in processing as well. The first thing you'll see here is the ground control points, and these are called propeller arrow points, and so we placed 8 of these total at the highest and lowest points of our study area to get the maximum correction from it. And what's also nice is when you set these down, you can press that button and it automatically starts collecting course data. So by the end, each of those individual ground control points have a fixed course location, which is really nice. This is the terrestrial LiDAR unit, which is a Ferrofocus S350. It's capable of taking up to about 975,000 points a second. It's a very common tool that's used in the surveying industry right now. Also, it has an integrated color RGB camera, so that's really nice too, because your point clouds can come back and be visualized really nicely with that. And we used that primarily under the bridge. For above the bridge, we used our aerial LiDAR unit. Here's a picture of the drone setup. It's a DJI Matrice 600 Pro, and this is the LiDAR unit, which is a Phoenix Mini Ranger, which is capable of taking 100,000 points a second, which is a lot of data. And so here we have it set up, and in the back you can even see the Sony a6000, which was set up nadir, looking straight down to produce an orthometric photo that was up to date on the site. Here's the drone set up and ready to go, and pretty much at this point all that was left was to set up our communications to the drone with this wireless antenna so we could get a live feed of visuals of what the drone was doing, and as well as also seeing what data we were collecting on the fly to get an idea of how good that was going to look. Lastly, we set up a quick flight plan. This was such a small site, the flight really didn't even take 10 minutes to get a lot of really good dense coverage, flying at like 6 miles an hour. Normally you might set this up before you go out to a site on the field if it's bigger and more complex. But this was so small, it was really, really quick and easy. And at that point, we were ready to take off and collect our data.
Alright, now we're going to talk about our data comparison between our LiDAR dataset and our photogrammetry dataset models gathered in the field. Starting off, we're going to talk about the LiDAR dataset, which is here. As you can see, it's a very wide field of coverage, with the top and bottom being the surrounding forest and the middle section in light blue being the bridge that we are surveying. The kind of red, orange, and yellow splotches are trees recorded. These are all classified by elevation here for the symbology. And those lines that are displayed now to the right of the bridge are actually power lines, where those yellow splotches on top of the bridge are cars passing by. Overall, the LiDAR data set was very smooth, returning a very low variation among z-values, leading to a very smooth overall surface. Moving on to the photogrammetry data set, however, you can see the surface covered is a lot smaller than the LiDAR data set. Additionally, it's a much rougher surface, especially when you look at the bridge, at the edges and around the water. There's a lot of variation that leads to a very rough looking surface, almost like a mashed potatoes. It's not a smooth surface like we're wanting. Additionally, there are going to be some errors around power lines and trees, especially with photogrammetry. So this here is a clipped LiDAR data set. We clipped it only to the bridge, displaying 800,000 points here out of 13 million. The red and orange splotches on top of the bridge are going to be cars passing by again, but overall, a very high quality and smooth LiDAR image here. Whereas when you compare it here in a second to the photogrammetry data set, you can see that especially on top of the bridge, much more variation, much rougher looking surface. This is mostly due to the estimation of the algorithm and predicting where exactly the surfaces are going to be on a bridge. The issue with this photogrammetry you see here is that because the bridge is a very kind of monolithic color scheme, same thing with water, it has trouble kind of tracking where in the image the bridge is. So what this leads to is in these two comparison tables, we see that between the LiDAR point cloud and the photogrammetry, the X min max, Y min max ranges are actually very, very similar. There's only at max a 2-foot distinction between the LiDAR point cloud min max and the photogrammetry min max. This, however, is very different with the Z values. The point densities are going to be lower for the LiDAR point cloud than the photogrammetry. However, when adjusting for the lower point density, the point spacing for LiDAR is actually going to be lower. It seems higher here, but that's mainly due to the lower point density with the LiDAR point cloud. When that's adjusted, there's actually much lower density. Now, on the main benefits of LiDAR, the biggest things we're going to see is, first off, is going to be lower point density. It's easily improved and more accurate. Additionally, it's also going to be lower point spacing. This is because it's an active sensor that's actively taking measurements, whereas photogrammetry is more of an estimation than algorithms using based off of a series of images. LiDAR also tends to have higher equipment costs and larger file sizes, leading to some limitations in use, especially with non-professional uses. While LiDAR does tend to perform better with smooth surface, water, and vegetation, photogrammetry does not. That's again mainly due to the cause of these kind of monolithic structures being difficult to capture.
For the gamification process, we made multiple attempts at creating an interactive model from our point data. Our first attempt, we put the LiDAR data into Recap and made an RCP and an RCS file, which was then put into Autodesk Civil 3D, but then we found out that Civil only exports as drawings and no longer supports FBX objects. Thus, we could not create a 3D model to put into Unity. The current results we got from using Unreal Engine is a point cloud that we can walk through by using a floor for the character to walk on. And our reasoning for not creating a better interactive model is that we received our data late and our team is inexperienced with the programs we use to create this interactive 3D model.
Lastly, I'd like to talk to you guys about some of the conclusions from this study and what we've learned from this project. Our hypothesis was, by using LiDAR, will we be able to improve the spatial accuracy of the data collection process for TXDOT alternative project planning methodology? To answer this question broadly, I think that our group can probably say yes. we were able to improve the spatial accuracy of the data. This is primarily because the LiDAR method uses an active sensor with known distances. The photogrammetry method is using a passive sensor, which is largely estimating the location of the points that it creates. While this fact may already be known in the industry, it's nice to see this point proved again for a hypothetical TXDOT application. It's also nice to see contractors like HTS Solutions doing this because they do these types of jobs all the time, and this type of data can be very powerful for people in a variety of applications. Our biggest takeaway is that photogrammetry is better for quick visualization of a site, but for infrastructure design, LiDAR is far superior because of its increased accuracy, especially with consideration to infrastructure surfaces, water, and vegetation. As far as the future of our work goes, there's a lot of things that could be done. We haven't even begun to utilize the terrestrial LiDAR set that we have from under the bridge. That could be used for a ton of different applications. We could also compare the accuracy between LiDAR and photogrammetry by taking actual structural measurements on the bridge. Or we could use the VGM tool, the Variable Grid Method tool that was designed by the National Energy Technology Laboratory, to assess the data uncertainty on both of the models. Those are all potential plans that we have for the time being, and maybe even try to turn this into a paper by doing some more intensive quantification and analysis. I hope you guys have enjoyed watching our presentation. I really appreciate you guys listening. But lastly, I'd like to say one last thank you to HTS Solutions, because without them, we wouldn't have been able to do this study, and they provided us with some really, really high quality data. Thank you guys.